So now we've done the unboxing and the evaluation. You know, we set it up on the bench and we hooked it all up and we applied voltage to it slowly, you know, so it doesn't go up in flames. But now we have to do the investigation. I want to see, now that I've got power applied to this thing, that I'm going to actually take some voltages and just see how this thing is behaving. The thing I want to really bring to your attention is that when I read the voltage on a lead on a capacitor and then go to the matching capacitor in the other channel, the voltages should have been the same. And they're not, because the leakage through these capacitors is dragging down the power supply. So the voltages are going to be all over the place. They should virtually match, you know, within a couple of tenths of a volt, but they don't. So this is already an indication that this thing is going to have to be totally recapped. And in order to basically walk you through that in this investigation process, we have to go back to the lab.
Your main objective with checking voltages right now, where are you going to go first?
I'm going to go right to the source, okay? I'm not so much interested in the transformer yet, because that's, of course, where the high voltage AC is coming from. The high voltage AC coming off of the winding, if you will, is going to the rectifier tube on the plates. So ultimately what we want to look at is the cathode. And with a 6x4, the cathode is common. I'm doing this because that's the cathode, and it's got a plate and a plate with the cathode passing between them. So you got high voltage AC here and here. It's basically a full wave rectifier diode. What it's doing is it's basically energizing one plate, then the sine wave goes the other way, energizes the other plate. So we end up with a high voltage ripple coming off the cathode, which goes to the first capacitor. In fact, you pointed out this which is kind of cool, and because it's on, I'm not going to be sticking my fingers in here exactly, but you've got a ground rail that runs through everything here. So it's, the chassis is ground, but it has a rail up here that's basically chassis ground throughout, which is convenient. The rectifier tube is right here. It's a 6x4, and it's a 7-pin tube. The filament wires, or the low voltage AC, if you will, for the filaments is actually these blue and white wires. You'll see those throughout. If it's a blue and white wire, then that's the filament voltages. One thing that I have also noticed is that, yes, okay, there's a 6x4, but the rest of the tubes in here are 12 something something something. Well, 12 is supposed to indicate the filament voltage, but the filament voltage throughout this chassis is only 6 volts. So you're thinking, okay, well then we've only powered the tube to half voltage. Well,
I think I know what you're looking for.
Yeah, I'm looking for those schematics. These came out of my RCA vacuum tube manual from long time ago. Yeah, that one right there. And what's really kind of funny, if you will, is that the book is broken. Okay, I haven't got any bookbinding tape to take care of this, so I've been taking very, very special care of this. What year was this? November 1966. Yeah. The book breaks in half, okay, because it's just wore out, but it was turned a lot to this section of the book. Well, as it turns out, the section of the book are the 12AU7, AT7, and the 12AX7. 12A something tubes are everywhere. So what I've got here is basically just a schematic. The schematics are identical, okay? It's just that the 12AU7, as I might have mentioned earlier, is a medium amplification factor tube, medium, okay? Which means the gain is medium. But the 12AX7 is a high amplification tube. And it's not surprising that it would be at the beginning of the input to the circuit throughout, because the first stage in most any amplifier is going to be the highest gain of any stage in that amplifier. The idea being is that the more you're going to get more noise with more amplification. So they put that at the beginning of the amplifier stages, and it gets less and less, still increasing, but less with less gain. And what happens is that the noise that's generated, you wouldn't want more noise generated at the output of the amplifier than you would at the beginning. Okay, well, the amplification factor for a 6AV6 is 100. So, as I said before, the first stage of gain is going to be on the order of 100. Each subsequent tube is going to be less gain, but still providing some amplification. Okay, confused? Well, that's what the rewind button is for. Yeah, like I want to listen to that again. What I want to do is check the voltages throughout, because that can be very telling in a circuit that is this old. So looking at the meter, ground wire is attached. What I want to do is first look at the output of the tube, the rectifier tube, and in this case I've got 292 volts DC. Now it's going to be attached at the other end of one of these wires to the capacitor. The voltage coming off the rectifier tube is going to a capacitor, which is basically filtering that with a reference to ground. The next thing it does is it goes off to a dropping resistor and then doubles back to the other capacitor in the same can. So what you end up with is what's called a pi filter. You've got a capacitor, a resistor, and a capacitor. So it looks like the letter pi. And that's where it gets its best filtering, because as you add capacitors to the power supply, you filter more and more of the AC ripple out of the DC. Case in point, let's just take a look here for a second, okay? There is the 292 volts DC, but the AC on that line, it's below the ability of this meter to read it, which means that filter cap is doing a pretty damn good job. So that's going off to a resistor, and it comes back to this capacitor. There's no AC on that, but it's also dropped down to 246 volts. This is going to be the first high voltage source for tubes in this amplifier. It's fairly clean. Goes through these resistors, and there's actually two resistors coming off of there. Each subsequent dual capacitor in this circuit is going to have a lower and lower voltage. The DC is already clean, so that's actually a pretty good sign. After these first 3K resistors, well, they're going to be going to different plates in different stages of the amplifier. Okay. And we can figure that out by going to the plates of these individual tubes. What I wanted to get through the circuit this way, and then look at the actual plates on the tubes and see how they're behaving. This is the next stage. That's 207. This is after the first dropping resistor and the second dropping resistor. Okay, so we got 206, 207 there. Okay, and then this next capacitor down here after, see, what is that, a 30,000. Okay, so now the voltage is at 117 volts. This is the end of the line for power, and that's 85 volts. Now we're going to go backwards now, actually forwards. We've went backwards through the power supply. Now we're going to begin. Want to look at this first stage. Or actually, there's going to be another resistor right here, 100K. All right, so that last capacitor in the power supply was 85.5, but the plate voltage on this first tube, which is going to have the most gain, is 56.8. This tube has actually got two triodes in it. It's a 12AX7. Pin 6 is the plate. So that's the DC voltage, about 57 volts on that plate. And then this plate over here is 60. So 56 and 60, pretty close. All right, and really the only fix for that is to just tweak the resistor going from the power supply to that plate. But I really don't see that as an issue right now. But now this should actually have no DC on it. I've almost got 1.5 volts on there. I'm sorry, that just shouldn't be there, because the input to that second tube, it's got an impedance resistor on there, 300K. Consequently, you know, that means that there's at least 1.5 volts across that resistor. I mean, there really shouldn't be any DC on there. That tells me that with 1.5 volts on one side and 60 volts on the other side, that capacitor is leaky. Let's check this one. Okay, same thing, stage 1 to stage 2, 57 volts on the plate. This should have 0 because it's got that resistor to ground, 1.7.
Capacitor
But
strike again.
I'm not surprised.
Okay.
I'm not surprised. Something this old, yeah, the capacitors there are leaky, but it also didn't go up in flames when we fired it up. And one good thing as well, because I'm going to take this tube cover off. The tube, even the first or the second stage, the tube, I can hold my hand on it. So it's not so bad, but tubes that have too much DC on the grid, is going to over-bias, or maybe under-bias, depending on how you look at it. That tube should be at near cutoff. And with a positive voltage on the grid like that, it isn't. It's not going to be there. So, and that's the beauty of this circuitry, because this is like you can get to everything. Replacing these capacitors is going to be a cakewalk. Let's just check the stages of the playback amp, just for shits and giggles. So this is the plate of the second stage, second tube, 45 volts. All right, that's nominal because it's going to have less gain. So it's not going to have as much voltage on the plate to get it to work. But what's coming out of that capacitor to the grid of the next stage?
I'm going to say 1.8.
1.8 for a leaky cap with a 45 volt input?
Okay, fine, 1.3.
All right. I don't want to discourage you.
All right.
All right. But the capacitors going from stage 1 to stage 2 are 0.05 microfarad. From stage 2 to stage 3, they're 0.1. Okay. Now, that is closer to 1 microfarad than 0.05 is. 0.05 is here, and 1 microfarad would be there. Okay, but 0.1 to 1 is going to be more like this. Okay, so what happens is that, okay, it's technically a larger capacitor. So a larger capacitor, if it's leaky, is going to probably have more leakage.
Okay. So
now, that said, now what do you think the voltage is?
I'm going to say 9 volts.
Which is why I don't give them an allowance.
I don't know numbers.
Okay, again, 45 volts going in. Okay. You want me to guess?
Sure.
I'm gonna say close to half of that. I'm gonna say 22 volts. I'm gonna say 22 volts going to the grid of that next tube, which is, it's on the verge of dangerous because the tube is probably going into saturation. Okay. So here we go. Coming out of that, 21.5.
Okay, fine, you know what you're talking about. That's why I'm not speaking very much right now. This is like way out of my element. All I'm thinking of is the fact that this...
I know what you're thinking of. You're thinking that, hey, I'll get Dad to fix this thing, and then when he's not here anymore, it'll be mine.
Halfway correct. Hey, I'll get Dad to fix this because I don't have the time to do so.
Uh-huh. Well, yeah, Dad's retired, so Dad's got time, huh?
Yes.
You know? So if I had all this amount of time, then why is it I'm the one that always has to put the trash out by the street? Just asking. Okay, so that capacitor, let's look at this one over here. Okay, basically the other triode in the same tube, it has a plate voltage of 39.4. Okay.
The other one was 42, yeah?
This one was 45. Okay, so that right there should tell you something.
All right.
Okay, these capacitors being leaky are dragging down the power supply.
Yeah. Yeah.
Okay, we need to fix it as soon as possible. So this one, what did we say? 39.4.
What microfarad is it?
It's same. I mean,
okay.
It's basically 0.1 and 0.1. This was 0.05, 0.05. This is 0.1, 0.1, going from stage 2 to stage 3. Okay, so the capacitor on the grid of the next stage, stage 3, was half of the voltage going in. So if that's 39.4, you think, you know, depending on how leaky it is, it doesn't have to be as leaky as the other one, but I'm going to guess 39.
39?
39, because it had 45 on the other one, 39, so I'm going to say 17.
I'll do 17.2, Alex. Or Bob Barker, right?
Yes, it's going to be the closest without going over.
That's right.
Okay, let's see what it is. 26.
Oh my God.
So you still win because you got closer than I did, but 26 with 39 going in, that's
a bad cap.
Yeah, bad, naughty. Stand in the corner. Okay, so that's going into stage 3. Okay, stage 3 to 4 is plate voltage right here. Don't worry about it.
You got audio hooked up.
Yeah, it's basically saying, hey, don't touch me there. Okay, so I've got 77 volts on the plate there. Okay, and so this is going to be the other channel at 75. So at least 77 and 75 is close.
Sure.
That should be good for something, right? Well, let's find out. Now we said what?
77.
77. And this is going into the last stage, 62.
Now this isn't going to affect anything plugged into it like these speakers, right? Because these are active monitors.
Well, you know, that's a very good question. I mean, if we were actually
DC
pumping
offset,
raw
right?
DC into these speakers, that could be an issue. Well, let's just check that real quick. Let's look at the output and see if there's any DC on there.
Okay.
None.
Oh.
0.015.
So there's a capacitor doing a lot of heavy lifting right now?
Yeah,
On the near end circuit?
on the very end, which we haven't got to yet.
Okay.
Okay. And then the other channel is 0.03. So
Wow. That's really good in comparison to what numbers
that's
we're
really
seeing.
good. So yeah, we probably should have checked that before we hooked the speakers up. Okay, and they're powered speakers, by the way. You can't see them because they're over here out of camera view, and we don't advertise for Rocket. So now this last tube, I'm just looking at this. This is wired differently. There are no capacitors coming off the plate to couple the audio out. It's just basically power supply DC going to the plates. So that 212 volts on the plate, and of course it's hardwired to the other plate, so it's going to also be 212 or within a couple of points. 212.
Spot on.
Okay, well what's happening here is that last tube stage, those two triodes that are in there are actually what's called a cathode follower. So instead of using that tube the way these other tubes were operated, schematic, okay, where in the typical triode, we'll just talk about one side of this, the plate is usually going to have a high positive voltage on there. The grid is usually biased to below 0, okay, in order to get the tube to cut off, depending on the class of amplifier it's operating in. But if you take and put no voltage on there, none, then current is going to flow. It's going to want to flow with a high potential like 200 volts on the plate. You're going to want to get some electrons flowing off that cathode to that plate. But what you have to do is to get it to shut down just enough to where it doesn't conduct. So you put a slightly negative charge on the grid and it will actually cause the tube to shut off. Unless you're going to operate in a Class A, I think I'm getting this right, but if you're going to operate in Class A, then you might even put a slightly positive voltage on there and it's conducting all the time. That way, when you apply the actual signal to that grid, then the tube is going to be operating in the linear portion of its curve. In looking at
I'll scan
this chart right here, depending on your plate voltage and then the plate current, if you will, is going to be determined by how much grid bias you have or don't have. All right, grid voltage is here, -2 volts, -4, -6, -8, so on. Okay, you notice how it's really a pretty decent straight line with 0. Remember, I said that the tube will conduct with no grid voltage on there. So it'll want to do that, but it's going to be kind of hard to control. So by applying 2 volts negative to the grid, then what happens is that the tube is going to behave with a certain kind of plate voltage, and we're operating, what do we say, 212, so it's going to be in this general area here. Let me get my 6R pointer. Okay, so at 212 volts, we want to operate in the linear portion of this tube characteristic. A certain part of this line is actually going to be fairly straight. That's where we want to be, because when we bias the tube to a specific spot, if you will, then any amplification that occurs with a signal on there, tone or music or whatever, okay, it's actually going to be rising and falling on that linear portion, and that you don't want certain signals to be louder than others, so you want to try to operate in the linear portion of the tube. So 212, we want to be in the linear portion, so really -2 has got a fairly linear portion at 212 volts on the plate. Okay, and we can operate in that range and draw between 25 and 30 milliamps. So
how do you read the milliamps on a tube then?
Well, in order to know what the milliamps is on a tube, you'd have to put a meter in the circuit. You'd have to lift the lead off the power supply to that tube, put a meter in series with it, and then you could actually read it. And if you want to get it really, really accurate, that's the way to do it. Okay, but then you've got to have the ability to be able to change the bias so that you can control to get those plates dead on. Okay, They never really intended that. They just want to operate in the linear portion. And if you can get the gain structure right, it's going to be fairly accurate across the board. So, you know, and when they talk about, you know, the, you know, with the frequency responses, you know, and it's flat from 20 to 20K plus or minus 5 dB. Well, you know, flat from 20 to 20K sounds really, really good, but not plus or minus 5 dB. It's going to be all over the place.
Sure.
All right. The typical human ear can hear the difference between 3 dB. It's like, play it 7, okay, play it again, plus 3 dB. I can hear that. Okay. A trained ear can get down to 2 dB difference, sometimes 1 dB difference. Would you care to speak to that?
I used to. I don't know if I can do that anymore.
What?
Exactly.
So, in any case, that's what you're going to be achieving with the tubes. But so I've really got into the weeds on that. I'm not sorry, okay? Because in some cases it's important.
We're trying to give you content that you don't often see in other places.
Well, okay. So that almost sounds like a microphonic tube. But it may just be a loose connection on the tube.
What tubes are? We'll find out later, but I wonder what tubes are in this thing.
Oh, you mean what brand?
Yeah.
Well, I don't know.
Shall I turn off the unit, or?
Huh?
You want me to turn off the unit? Oh.
Why?
Okay.
It's that's what I think.
Japanese.
It is Japanese, but it says Matsushita.
Oh, Panasonic.
Okay, Matsushita Electric Industry Company Limited.
So they got Panasonic tubes and a Denon player.
I don't know. It's all Greek to me.
It's Japanese, not Greek.
Oh, okay. My bad. So, okay. So let's see if I can get this back in there the right way. Okay, that's the volume control on the output. Okay, but here's what's interesting to note. Okay, and that is I'm cranking that knob back and forth, and it's not getting louder or softer. It's just making noise. Well, what we have there is an intermittent white noise generator. Okay, sounds like some of the 78 RPM records in my library. That's DC. So what's occurring here is that there's so much DC leakage in this amplifier that it's got as far as, well, the third stage of this amplifier. If it could be tone, it would be just a constant tone. But in this case, it's just noise, the DC noise that's being funneled to the next stage. And
one thing that I noticed is it looks like the balance pot gets the signal first, and then it gets chained over to the volume.
Yeah, that's a good point. Good call. Because the previous stage, basically the output of that through its capacitors that are leaky goes to the balance pot first, and it comes in on this side of the pot. This is the wiper. So this is the input to that pot. You notice there's no wire on this side. So it's really just a rheostat, okay? But the other channel comes in on this pot. So when this is turned counterclockwise, then the wiper on this one is basically at this potential. And this wiper is as far from this connection as possible. So to turn it back the other way, now this point is on the wiper, and this one is far away. Try to get that centered, so that way the signals that are coming into here are basically appearing at this yellow wire and the green wire, which go right next door to the volume control. And then the volume control wiper, which is also green and yellow in this particular case, is basically taking the signal, or the absence of it, to the next stage. The problem is that there's DC appearing at the balance control and then feeding the volume control. So there's already DC present.
So with all these capacitors on the playback section running into this and then the volume pot, there's no way to escape the DC from feeding into the outputs because the capacitors are bad.
Because the capacitors are bad, replace the capacitors, problem solved.
Yeah. But the thing is, though, is that we're not getting pure DC to the output.
At the output, but that's because partly because that last stage, that 12AU7, is a cathode follower.
Okay.
Okay, because the output to the speakers leaving this unit is not on the plate side with capacitors. And by putting full voltage on the plates for that particular tube schematic, these plates are getting full voltage, so they're pulling the electrons out of these cathodes here. The signal is going into the grid, and it's modulating that, if you will, and it's being amplified. Not a lot, okay? Because first of all, a 12AU7 is only a medium amplification tube, okay? But by the same token, all that's really going to be coming off of these cathodes, with capacitors, mind you, is just the signal. So even if it had DC leakage, it's not going to amount to much, okay? And in this case, hardly anything at all, which is in fact a good thing.
It's a saving grace.
Quite frankly, I'm impressed, because if I had to think about it, that's the way I would have done an amplifier. I wouldn't want to risk 200 volts going into my powered speakers.
Or your amplifier.
Or my fingers, for that matter. I mean, it'd be a bad day.
So we need
the output, which is going to be on the cathode with a capacitor coupling the signal out. So what is the DC value? Now, and of course, it's coming off the cathode, so it's not going to be a lot of DC voltage. All right, but I'm more interested in how much the capacitor is blocking the DC. And coming off of that cathode, 53 volts. Okay, and then this is the actual output.
Oh, okay.
0.02.
So that's a healthy capacitor.
Yes, I would call that a healthy capacitor, but it gets changed anyway. Okay, on this side, on this cathode, 36 volts. Now there's something very interesting. That's 36, 37 volts. But on this cathode, it's 54. It's almost twice as much.
Is that because the capacitors in the earlier stages are bringing the voltage down?
I wouldn't think so, but I can't rule it out. All right, but that is significant.
Yeah.
Okay, I'd almost be willing to put a microamp meter in there or a milliamp meter in there and just see where the current is going. Okay, but that is a factor. Okay, also it could be that tube has just gone soft.
Okay.
You know, because it's just not conducting. So 37 volts. Wow. Okay,
yeah.
And yet both plates are getting the same voltage at 212 volts. So let's look at schematic. Grid 1 is pin 7. And grid 2 is pin 2, so 7 and 2. So let's just look at the DC voltage on these grids. Coming in here, 39, almost 40 volts on the grid going to that tube. We're trying to figure out why the cathode current is so high. So 39 volts there, and that was pin 2. Pin 7, all right, that might explain it. The grid voltage is almost 56 volts on one and 39 on the other grid. All right, well then let's look at the correlation. Okay, if the grid over here is 56 and the cathode is 54.8. Okay, 55.8 on the grid, 54.8 on the cathode. Interesting. Grid over here is 39.6 and the plate is 37. So there's a correlation there. The amount of DC getting into those grids because of those leaky capacitors is causing excessive cathode current.
Ouch.
Okay, from the in that particular tube. So, and then of course the output. Fortunately, these caps are eliminating the DC coming off of there, so that the actual output of the last stage of the tube going to the powered speakers on one channel is 0.02, and on the other channel, 0.02.
Okay.
So those capacitors are doing a job, but I tell you what, they're taking a beating. They are really taking a beating. So they're going to get changed too. That's the playback section of this RP unit. It needs help.
So it sounds like I need to leave you with this unit.
Yeah, I mean, it's not like I had anything better to do.
Good. I figured you might enjoy this.
Well, I look at it this way: if I can get through something like this in a couple of days and have all of my fingers intact, I'm a happy camper.
Me too.
I'm going to stop right here and interrupt myself, okay? Because there's really no point in moving forward on this. These voltages are just all wrong, okay? Clearly the capacitors are leaking so bad that they're dragging the power supply down, and these voltages that are supposed to be a certain value aren't. So in the next episode, I'm actually going to go ahead and get deeper into this and actually take the readings and check, the signal through the power supply in order to figure out, how badly it's affecting the power supply. And then I'm getting interrupted with the unannounced arrival of a lost puppy. So, all bets are off on this. And speaking of bets, I got a good one for you. Patreon. If you go ahead and pledge on Patreon to 6R, we're going to make available to you unedited episodes that will actually take you deeper into the detail. If you like the weeds, you know what I'm talking about, well, we're going to take you there. And those episodes are available to Patreon subscribers. Also, eventually, we'll have some merchandise that we're going to make that available. And then service manuals. Just to name a few, we'll have some service manuals that we're going to upload that you'll have access to, PDF files. It's going to help you out in the long run. So thanks for watching. I'd like to hear from you. Give me your comments, all right? And hit that subscribe button, please and thank you.